In this video, we're going to work through the solutions to our isomer practice problems. And I'm going to start with our nickel example. I've got two cyanide ions and two chloride ions coordinated to this nickel. So it's only four things. And um, if if this was a square planar arrangement or a tetrahedral arrangement, we would have very different possible isomers with this. And so I'm going to look at tetrahedral. That's what it is. And then I'll speak briefly to the square planar version. So if I have this arrangement, I'm going to build out a just basic structure for a three-dimensional tetrahedral compound right here. I'm going to add my chlorine and my cyanide. And so I'm going to put in my chlorine first. And there's lone pairs too. Now, when I'm choosing my cyanide, I have a choice. So that cyanide ion looks like a carbon triple bonded to a nitrogen, and it has a lone pair on both the carbon and the nitrogen. So this is an example of a ligand that can actually coordinate through either one of these atoms. And so I can have the nitrogens coordinate, or I can have instead the carbons. And so this would give me an example of those coordination isomers. I'm sorry, linkage isomers. And it's the real difference between these is just whether or not it's the carbon or the nitrogen. Now I'm drawing this in 3 dimensions. And now if this was square planar, or if I was drawing it in 2 dimensions and I know it's tetrahedral, but I forget to think about it in 3D, it would look like something that was in the same plane. So I could draw my chlorines at the top and bottom. And I'm just going to choose one of my linkage isomers for this one. And I can imagine seeing this as a trans isomer if this is square planar. And then I can rearrange this so my chlorines are 90 degrees apart. And I would have the cis isomer. But this is only for our square planar. And so if I'm drawing a tetrahedral structure in 2D, like I would a Lewis dot structure, and I'm looking for isomers, I might mistakenly decide there's a cis and trans isomer for my compound. But when I look at the tetrahedral version of this, no matter where I put these chlorine relative to one another, they'll always be 109 degrees apart. And so there's no cis and trans isomers possible with the tetrahedral geometry. So be careful there. For our next example, we're going to look at iron coordinated to 3 ethylene diamine molecules. And so this is going to give me that ethylene diamine is going to be a bidentate ligand. It's going to have a nitrogen and these carbons linking 2 nitrogen atoms together. And so I'm going to be coordinating to my metal through those lone pairs on the nitrogen. I'm going to abbreviate this as a nitrogen linked like this. You'll also see this abbreviated like this or even like this. So with that ligand in mind, I've got 3 of them that I can arrange around my iron. So I am going to build out my standard octahedral geometry first and then plug this in around it. So I'm going to start with my nitrogen at the top going to the side here. And I'm going to have the one on the bottom coming out front. And I'll have the one heading towards the back come around in the same plane, so in the equatorial plane. This is going to look kind of like a propeller, honestly. And so looking at this, I don't have the option for a linkage isomer. I don't have the option for a coordination isomer because I haven't given the possible counter ions. And this isn't FAC and MER because I don't have 3 of the same thing and then 3 different things. And I can't do cis and trans either. So I'm going to check this for an optical isomer. And I'm going to do that by drawing the mirror image. So I'm going to imagine there's a mirror here that this is reflecting in. And I am going to draw this as best I can to perfectly mirror it. So I'm going to have my plane, and then I'm going to have one coming out this way and one going back. And I'm just going to copy this in a sense. And when you're drawing this, it's going to feel like you're drawing the exact same molecule. But now we're going to do the work of rotating this and redrawing it. And so what I need to do is rotate this whole thing 180 degrees. And so that means that this nitrogen right here is going to come to the other side. They're going to swap. This one up in the front is now going to go into the back. The axial positions will stay the same. And so now when I redraw this, let's see what it looks like. So I'm going to redraw this in the same conformation. So you notice that I'm spatially arranging my bonds exactly the same as I did at the beginning, so it's easy to compare. If I switch to an arrangement where I've got 2 going back and 2 coming out now and compare it to something where I have 2 in the same plane, 1 going back and 1 coming out, it's just going to be hard for me to reconcile the images. And so now as I rotate this nitrogen that was in front here goes all the way to the back. So I'm going to draw this one in the back. And I know it links to the bottom. So I'll draw that one right here. Looking at the one that's closest to the mirror is going to come around 180 degrees to the back side here. So this nitrogen is coming here. So I'm going to draw it right there. And I know that one's linked to the top. So I'll draw that there. And that leaves these 2 right here. They're going to rotate around. This one in the back's coming all the way to the front, and this one on the right-hand side goes to the left, and they're linked together. And so now I'm going to try to compare this one and this one and see if they're superimposable, if they're the same thing. And so I'm going to do this by drawing this like this. So this green one is coming here. I'm going to color coordinate these. I've got a yellow. I'll do a yellow here at the top, and I'll do a blue coming out and down. So now I'm going to go find the one that's going down. I think it's helpful to look at these from the axial positions. It's now going back to this nitrogen. And if I look at the one that was going up before, right here, instead of coming over to the left, it's actually going over to the right. And lastly, I'm going to take a look at the one that's in the equatorial plane. It used to go towards the back, and now it's coming towards the front. I can't superimpose these. So these are optical isomers. In this example, we have cobalt and diethylene triamine, along with 2 chlorines and a bromine. And now we actually know one of our counterions. It's a chlorine ion. So this diene is going to be a nitrogen. And I'm going to use abbreviations here for these stick drawings. That is connected by 2 carbon atoms on each side to another nitrogen. And so we find that this ligand is a tridentate ligand. It's got 3 spots where it can donate electrons to the metal ion. And so it'll actually take up 3 of those spots in our octahedral complex. So let's just draw one of these. Let's get cobalt in the middle. So I'm going to kind of just draw my skeleton here, and then I'm going to choose where to put things. I'm going to start with this nitrogen that's in the center right here at the bottom. So it's bonded to a hydrogen. And I'm going to connect it up here to these 2. And I'm just going to abbreviate these with these loops so we can get a sense of where this geometry is. And it's going to leave these 3 other positions. And so I'm going to put in a chlorine here, and a bromine there. Why not? So here's one option that I have for it. I can also then imagine an arrangement of this triethylene diamine that instead takes up a space where we go from the nitrogen here at the bottom, and then rather than going to 2 spots that are 90 degrees away from one another, so right here we've got this 90-degree angle, instead let's put those 180 degrees apart. like this. And now my chlorines can come and take a spot on either side here with my bromine. And what I've done is I've created a FAC-enmer and also a cis and trans isomer at the same time. And so if we look at my chlorines here and here, I have a trans isomer for these and a cis isomer for those chlorines. And then for my FAC and MER, I have the FAC right here. And I always flip these around in my head personally. And MER here. So I have that T arrangement for my ligand for MER, and I have that kind of corner style arrangement for my FAC. And so I have a couple different isomers here. So I have FAC versus MER, I also have cis versus trans with the chlorine. I also have another option. I can do a coordination isomer as well if I can, and swap out this bromine and chlorine possibly. And then that's going to give me I will no longer have the option for cis and trans isomers because I'll have 3 chlorine, but I'll just have the FAC and MER arrangements. And so I'm just going to draw one of those to show it. And then you can do the other one as well. Notice that when I'm drawing these isomers, I always draw my octahedral complexes exactly the same. And so choose a version that you like and do it the same way every time so you can easily compare between them. So here I'm going to do the MER again since they're right next to each other. So I'm going to add in my nitrogens and my abbreviation here. And then I'm going to put in my chlorines. And so you can see those chlorines now occupy MER arrangement as well, kind of in that same T structure that we saw.